So our next topic is constant voltage supply and constant power supply and constant current supply. So we'll see various power supplies. Power supply, voltage supply and current supply. Constant power supply, constant voltage supply and constant current supply. We need to distinguish all these three, and we need to develop them with the existing equipment. At least we try to simulate them under what conditions the given supply is called a constant power supply or a constant voltage or constant current supply. I mean, how to tune them, how to manage them, or how to design them is a matter of discussion now. Okay, so to know that, we'll start with a basic example. I'll take a battery, a power supply. I mean, we call it as constant power supply. Why is it called constant power? We'll see. Okay. So before that, we need to know the basic terminology that is being used in electricity. So what is current? Current is rate of flow of electrons, Q by T. So how many charges or how many electrons are flowing through the given circuit is per unit time is called current. Okay. So next one, voltage is a work done on each charge. Work done on each charge. It's nothing but it is the energy supplied to each charge. So what does a battery do? Suppose you have a 5 volts battery. What does it do? It gives 5 joules of energy to each electron. Otherwise our pen cells 1.2 volts or 1.5 volts. What is that? So it gives 1.5 joules of energy to each electron, whatever that enters the battery. Okay, so now what are the limiting factors? I consider a 5-story building. A 5-story building, and each level there is a lift, and let's say the capacity of the lift is 24. The capacity of the lift is 24, and let's say it is taking 1 second to go and come back for each floor. So time of travel for each floor is 1 second, let's say. Okay, so now this is 0, 1, 2, 3, 4, 5. So from this level I consider the number of persons the lift is carrying as electrons. Okay, so I'll see how this current and voltage will vary. So as I go up and up, this is my voltage: 1 volt, 2 volts, 3 volts, 4 volts and 5 volts. Okay, so I'm giving certain amount of energy. Here it is potential energy in case of building, and in case of battery it is that is also some kind of potential you are supplying to the electrons. Okay, so this to this level it is 1 volt, 2 volts, 3, 4, 5 volts. So now, what is the maximum number that this can supply to first floor? It is 24 electrons per second. So per second it can supply 24 carriers. Here also 24 per 2 seconds. It takes 2 seconds of time. So what is current? It is 24 amperes. Here it is 12 amperes. What about here? 24 per 3 seconds. So it is 8 amperes. 24 4 seconds. 6 amperes. Okay. This is how voltage and current will vary in a battery. So if you want to gain, or if you try to grab more amount of current, voltage will fall down. That means the energy supplied to each electron will reduce. So what is that remains constant in this entire story? So it is the capacity of the lift. Is the control parameter. Let's say if this supports let's say 96 electrons, otherwise 48 electrons at a time to second floor, here also you'll have 24 amperes of current. Just because the maximum capacity is fixed, you cannot go beyond that. So that is why current is dropping as you go to higher and higher potentials. And if you see the product of these two, what is happening here? Let's see. With the rise in voltage, current is falling down. మరి ఓమ్స్ లా ఏం చెప్తుందండి? What is happening here? With the rise in voltage, current is reducing, falling. So the simple Ohm's law is not working out here. So what is the control parameter now? So if you see the product of these two, product of V and I, what do you get? If you multiply these two, work done per unit time is the power. Okay, so if you calculate power, what is that? Here it is 24, here it is 2 volts multiplied by 12, 24, 24, 24, 24. Watts. So this is called constant power supply. So here what is happening? So in this story, what is the independent parameter and what is the dependent parameter? Voltage and current. What is depending on the other one? Who is depending on?
Current is dependent on voltage.
Yes. Voltage is independent. Once you choose the floor, you are going into current modifies accordingly, changes accordingly. So if you have decided to go to third floor, your current is limited to 8 amperes. Right? So that is how. So how to write that equation then? I is proportional to V. Proportional or inversal? I is proportional to 1 by 2. So current depends on voltage. Voltage is the independent parameter, and the proportionality constant is P. P is constant, and that's called, so that is why it is called constant power supply. So what is happening? The amount of power supplied by the power supply is constant. It is 24 watts. So if you distribute all the 24 watts to 24 electrons, you'll get 1 volt per charge. So it's simple distribution. When if you distribute the entire 24 watts to 24 electrons, you'll get, each electron will get 1 volt potential. So like that, if you give entire your power to limited number of electrons, let's say 6 electrons, then each electron will gain
5 volts.
more voltage, more energy. Voltage means what? Energy supplied to each electron. Okay, so like that. So if you raise the potential, current reduces. So that the total amount of energy supplied to all the electrons is constant. Okay, so that's why it's called constant power supply. So in general, if you raise the voltage, current falls in a constant power supply. So now comes the case, I try to complete this circuit. How do they come back? I mean, once the charge carriers reach here, they have to come back, right? Okay, so for the time being, I'm using a slide. Here also I'm using the same slide. Who will come first?
Top 5 volts.
Why?
Snapping more slack.
It's more steeper. Slope is high. Okay, so that means what? How quick they can come back is decided by the voltage. So in this case, when they come back, the current is proportional to voltage. Higher the voltage, higher is the amount of current. Right? Here the carriers will move slowly, here they move quicker. So what is the equation? I is proportional to B. And the proportionality constant is 1 by R. So in this story, I mean, when they are trying to come back, what is the control parameter? I mean, what is that remains constant? It is the size of this slide that remains constant. If I use a shorter slide, here also current will remain same. I mean, here also carriers will come back quickly. Just because the length of this slide is constant, on the lower floors current is reducing, on the higher floors current is increasing, right? So that constant parameter is called resistance. So as long as resistance remains constant, current is proportional to voltage. So that is what Ohm's law tells. So once you fix the constants, you can write the equation in any format. So this is not a valid statement. V is proportional to I. And if you raise the current, voltage increases. Situation ఏదైనా ఉందా? If you rise the current, voltage increases. Is it a meaningful statement? If you rise the voltage, current increases. Valid. So this has no meaning in physics. Okay. So this has a valid meaning. Proportionalities. If you rise the voltage, current increases. Okay. So that's called Ohm's law. So now, what are the factors or parameters that this resistance depends upon? Length, width. Okay, so let's say some carriers are coming here. Let's say one carrier at a time, one electron at a time is coming. If I double the width, 2 electrons will come at a time. So this resistance is proportional to area of cross section. Now, the resistance is proportional to length. Resistance. More the area, less is the resistance. More the length, high is the resistance. This R is equal to, this is called a specific resistance. So is that clear? So if I double the width of this slide, current doubles, and if I reduce the length, then also current increases. Okay. So specific resistance is the resistance of the material with unit length and unit area of cross section. So that's just a definition, standard definition. How to get that value is take 1 centimeter wire and 1 square centimeter area. Then whatever resistance you get is called a specific resistance of that material. Okay. So now comes the question. So in case of resistors, if you rise the potential, current increases. Okay, so now we'll see parallel and series combinations of resistors. Okay. Right. Parallel and series resistors. Let's say I'll start with series combination of resistors. I'm taking 2 resistors here, R1 and R2. V is my power supply. So when I join 2 resistors in series, what is that remains constant? That is the current. So let's say there are 2 obstacles. So I can draw So there are two tracks. On highway there is a bottleneck traffic jam. Okay, so let's say this allows 10 vehicles at a time, and here maybe 2 vehicles, and here only 1 vehicle at a time can travel in this narrow road. And let's say this entire track is filled with vehicles. So how many vehicles can travel at a time? So even if all the 10 quickly travel and reach here, only 2 are allowed. So remaining 8 will stop there. And once you cross this and reach here, only 1 is allowed. Right? So and further, if you travel quicker, again you have to stop here. And if the entire track is filled with vehicles, what is the maximum rate? Only 1 person at a time. So the current is controlled by, current remains constant when the resistors are in series. Current remains constant. So here I is constant. It can be written as V by R or V1 by R1 or V2 by R2. And voltage, total voltage is sum of these two. So in the same example, so when you are joining two resistors, you have to ensure that area remains equal. So whatever difference you can show should be in the length only. When we are joining, you should ensure that width is common for both, because current is constant. So we cannot alter them. So here let's say here 2 volts will be dropped and here 3 volts will be dropped. So if the length of the resistance is smaller, lower potential will be dropped, and if the length is high, resistance is high, so high voltage will be dropped. So from top to bottom, entire 5 volts should be dropped, right? And we are connecting, or we are taking a series combination of resistors. So some portion will be dropped here and remaining will be dropped here. So the total voltage will become 0 by the time the carrier reaches the ground. Okay. So now, how to write that equation? So total voltage I am supplying will be dropped partially at this resistor, remaining part will be dropped at this resistor. So let's say V1 is the potential here and V2 potential drop here. So that sum of these two will be equal to total voltage. So now I use these parameters and substitute here. So what do you get? V is equal to IR is equal to, what is V1? IR1 plus IR2. So in total it is R is equal to R1 plus R2. So the total resistance in the circuit is sum of two resistors. And now I want to get the value of V1. What is the voltage drop at R1? How do you get that? V1 is equal to IR1. So V1 is equal to, what is I? I is equal to V by R. So in total it is V R1 by R1 plus R2, and V2 is I R2, V by R R2, V R2 by R1 plus R2. So voltage drop at first resistor is given by total voltage multiplied by fraction of the resistance. So the fraction of the voltage at 1 is obtained by multiplying the total voltage with fraction of the resistance. R1 by R1 plus R2. This is total, so fraction R1 by R1 plus R2. Okay. So the same way V2 is VR2 by R1 plus R2. Is that clear? So now I try to replace one of the resistances with, let's say R1 is 0. I am replacing the resistor with a wire, conducting wire. What happens? So entire voltage will be dropped at R2 because there is no voltage drop at R1. So I am replacing R1 with a conducting wire. R1 is 0. What happens then? V1 is 0. What about V2? V2 ఏమవుతుందండి? So entire voltage will be dropped across R2. Is that clear? So if I replace R2, R1 is intact and I am replacing R2 with a conducting wire. Entire voltage will be dropped across R1. Okay. Is that clear? So now I go for parallel combination. So when you take parallel circuit, let's say this is R1, this is R2, this is V. So what shall I do? I have to use two slides with same length. I have to use two slides with same length. Then only. So here I is equal to I1 plus I2. Total current will be divided. A fraction will be traveling through R1. Another fraction, remaining part, will be traveling through R2. So current divides in parallel combination and voltage remains constant. Potential difference between these two is constant. Okay, so V is equal to constant. What is that? IR, I1 R1, I2 R2. So now I have to substitute these values into that equation. So I is what? V by R is equal to V by R1 plus V by R. Okay, so what do you get? 1 by R is equal to 1 by R1 plus 1 by R2, or R is equal to R1 R2 by R1 plus R2. Okay. So now we have to get the values of I1 and I2. What is I1? IR by R1. So I R1 R2 by R1 times R1 plus R2. So it is I R2 by R1 plus R2. I R2 by R1 plus R2. Next one I2, IR by R2. So it is I R1 by R1 plus R2. Okay. So current through R1 is depending on the value of R2. Okay, I mean it also depends on R1, but majorly controlled by R2. The same way I2 is proportional to R1. Okay, so now I'll take these special cases. So I take R1 as infinity. Let's say R1 is infinity. Means I'm removing that resistance. I'm removing this. So what happens? Entire current will flow through R2. No other option. So check. What is the value of I2 when R1 is infinity? I2 is equal to IR1 by R1 plus R2. What is that value when R1 is infinity? R1 is infinity. You get infinity by infinity. So how to solve that? So whenever you come across infinities, try to invert them and get a 0. So keep the infinity terms in the denominators, not in numerator. What 0? Divide with R1. So what do you get? I2 is equal to I times 1 by I by 1 plus R2 by R1. When R1 is infinity, so I2 is equal to I by 1 plus 1 by infinity. I. So always your equation should speak. Okay. So the same way you can substitute R2 to infinity. So when you remove the resistance, entire current will flow through one resistance only. So voltage is already constant. Whatever voltage you supply will be dropped same manner across each resistance, because they are connected in parallel. So the voltage drop is constant for both. Here the voltage drop is different. Okay. So so what if I replace this R1 with a wire? Let's say R1 is 0. One of the resistors in the parallel circuit, R1 is 0. What happens? I1 is IR2 by R1 plus R2. This becomes I. R1 is 0, R2 cancels out. I1 is equal to I. So entire current flows through this. Okay. What about I2? I R1 by R1 plus R2. This is 0. So no current flows through the second resistor. Entire current will flow through the first one, which is 0 resistance. What about I? What is the value of I then? I is V by R. What is R?
0.
R1 R2 by R1 plus R2. So this is V by 0, which is infinity. So when one resistor in parallel circuit is replaced with a wire, entire current will flow through that, and the current is infinity. So if you join the two ends of a battery with a wire, infinite amount of current will flow through it and wire will burn down. Okay. So that is about parallel resistance. So what if I make R1 infinity? If I remove R1, what happens to series circuit? R1 is infinity. This is V1, this is V2. R1 is infinity. What is V1? V1 is VR1 by R1 plus R2. R1 is infinity. So I have to push R1 to denominator. So this can be written as V by 1 plus R2 by R1. So when R1 is infinity, this is V by 1 plus 0 V. So V1 is V. Entire voltage will be dropped. What about V2? V R2 by R1 plus R2. Then what is the value of V? Voltage drop across the circuit when you remove one resistance in series is infinity. It means no voltage will be dropped. Right. So our next topic is construction of voltmeter and ammeter. Right. Next topic is construction of voltmeter and ammeter. Okay. So you might have come across this galvanometer, which counts the number of charges flowing through it. Moving coil galvanometer or any kind of galvanometer. So if you have moving coil galvanometer, how does it look like? There will be a horseshoe magnet. Somehow, and a coil will be hanged, and when current passes through it, coil will rotate in the perpendicular magnetic field. So this measures the amount of charge flowing through the circuit. So now we have to use this galvanometer to measure voltage and current. So how to modify or how to convert this for our purpose is a matter of discussion. So what is an ammeter? It measures the rate of flow of charges. So how many charges are flowing per unit time is being measured. And one primary condition is whatever measuring device you are using, it should not disturb the actual circuit. Let's say in some circuit 100 electrons are flowing, and when you start counting, you're stopping and counting each and every individual. Then what happens? The flow will slow down. So the ultimate aim of any measuring device is it should not disturb the actual circuit, or it should not disturb the actual activity. Right? So we should use a device which do not disturb the actual flow of electrons, but it should count. Okay. So for that purpose, I am converting this galvanometer. So by the way, this ammeter should be connected in series, because we have to count the number of carriers flowing through the circuit. So we have to connect the ammeter. We have to cut the circuit and insert ammeter into the circuit, just like our water meter. What does it do? It counts the amount of water flowing through the pipeline. Elagandi, we use a simple turbine. The number of rotations it makes will be counted as a number of liters or whatever. Okay, the same way we have to use an ammeter to count the number of electrons flowing through the circuit. So we have to cut the circuit and insert ammeter. And ultimate aim, it should not disturb the actual flow, and it should count. So what I have to do? I have to use the galvanometer in parallel with a shunt resistance. This is called shunt. R is nearly 0, it's not equal to 0. If it is equal to 0, current becomes infinite. So nearly 0, so almost 99.9% current will flow through this, and 0.1% will flow through the galvanometer. So whatever reading I get here, now I multiply with 1000. Then I'll get my reading. So I count a fraction of the current flowing through it, let's say 0.1, and I multiply whatever number I got in galvanometer with 1000. I'll get the actual current flowing through the circuit. And at the same time, I'm not disturbing the actual flow of electrons. Almost 99.9% of the electrons are bypassed. So this shunt resistance acts as a bypass, so that major current will flow through that shunt resistance, and meter takes only a fraction of the current and scales it up. Okay, so that is how I develop this ammeter. So ammeter can be developed as a galvanometer in parallel with a shunt resistance. So this is called ammeter. So internal resistance of ammeter is almost zero. Ammeter should be connected in series. Right. So now what about voltmeter? What does it measure? Voltmeter measures the potential difference between 2 points. Let's say in this circuit, the voltage drop across the resistor need to be measured. Then what shall we do? So the voltmeter, whatever meter you are connecting, should not disturb the actual flow of electrons. So, and aim of the voltmeter is to measure the potential difference between 2 points in a circuit. Okay, so what to do? This should be connected in parallel. And how to develop that? I use a very high resistance in series with a galvanometer. So that when I construct the circuit, only a fraction of the current will flow through it. And I'll multiply whatever result obtained here with multiple. So that gives me an information about voltage drop, and it's called voltmeter. So voltmeter should be connected in parallel in the circuit, and a voltmeter is obtained by connecting a very high resistance in series with the galvanometer. So this entire combination is called voltmeter now. And internal resistance of voltmeter is infinity. So now let us see, let's say I have a circuit like this. What happens if I connect a voltmeter here? What voltage will it measure? I'm connecting it in series. Actually, it should be connected parallel. I'm connecting it in series. What voltage will it measure?
The voltage drop across
How and why? There is an R3. So what happens exactly? If you see this voltage, a part of it will be dropped here. Remaining portion, let's say if this is 10, let's say some 3 volts is dropped here. Remaining 4 volts is dropped here. Remaining 6 will be dropped here. But now what is happening? I am connecting a voltmeter, that too in series. It means what? In terms of resistances, this is an open circuit. Internal resistance of voltmeter is infinity. So it acts as an open circuit. So when the circuit is open, no current flow through this. So end of the story, there is no current flow through R3. So the entire current will flow only in this loop. So if you connect a voltmeter there, you will get the voltage drop across R2. So R3 will be bypassed and you will get the voltage drop across R2. And if you remove the resistance and check, you will get same result in both the cases. You can verify that. So take this as 10 volts and this is 5 ohms, 5 ohms, 5 ohms. So if these two are equal, let's say, otherwise 1 kilo, take 1 kilo, all are 1 kilo ohms. So if R1 R2 are equal, we should get half of the voltage drop at R1, remaining half at R2. So our reading should be 5 volts with R3 and without R3 as well. Confirm it. Right, so when no current flows through the circuit or any component, that can be removed. So here the voltage across R3 is 0 because the circuit is open. Internal resistance of voltmeter is infinity. So now the same circuit, I connect an ammeter in parallel here, parallel to R3. So by mistake, I connect an ammeter in parallel. What does it measure? Ammeter is what? Internal resistance of ammeter is 0. So it acts as a bypass. So entire current flows through ammeter and effect of resistance is 0. What happens then? This resistance will become 0. This is a bypass, and R2 also becomes 0. Effect of R2 also becomes 0. Whatever entire voltage, let's say V is 5 volts, will be dropped here only. Let's say connect a voltmeter here. Connect a voltmeter across R1. Connect an ammeter across R3. So this will be bypassed. You get a short circuit here. And R2 is parallel to this entire thing. So this is a open wire. So that straight conducting wire will bypass R2 also. So entire this can be replaced with a direct wire. You understand this? So when you connect an ammeter in parallel, this R3 will be bypassed. This is short circuit. So this entire circuit is short circuited. R2 also will be short circuited. You will be left with only resistance R1. Confirm it. Right, so our next topic is constant current supply and constant voltage supply. Constant current supply and constant voltage supply. So what we have seen earlier is this. So here when you keep rising the voltage, let's say power is 30 watt. So when you keep rising the voltage, here the current is 30 amperes. Here it is 15 amperes, 10 amperes. 7.5 amperes, 6 amperes. So like that. When you rise the voltage, current reduces. This is what the case with constant power supply. So this is constant power supply. So in constant power supply, when you rise the voltage, current drops. So now I want to construct a constant current supply. Means what? A supply where whatever may be the potential, current should remain constant. Whatever may be the potential. So let's say I want 10 electrons. Can I supply? Yeah. So if this keeps on increasing up to 30 volts, I'll get 1 ampere current here. Right? So if I need 30 electrons, this supply can supply only 1 volt of potential to each. So if I limit it to 15 electrons, I get 2 volts. Right? So if I limit it to the least possible amount of current, I can go to maximum possible voltage. Right? So if I confine to 1 ampere current, 1 ampere current is sufficient for me, then I can supply 1 volt. I mean, each electron will get 1 volt. 1 volt, 1 electron is possible to grab from this. 2 volts, 1 electron possible. 3 volts, 1 electron. Up to 30 volts, 1 electron is also possible. So if I restrict myself to least possible amount of current, I can go to most possible amount of voltage. Right? So that is the basic idea in a constant current supply. Limit the current to least possible value, then you get potential value to any number. So then how to limit the current? I take a constant power supply and connect a very heavy resistance in series. So it allows very least number of carriers. It allows only 1 electron, let's say, at a time. It's very narrow, very high resistance. So even though the power supply is able to produce more electrons, right. So if I keep a very heavy resistance in series with a constant power supply, it acts as a constant current supply. Okay, so internal resistance of constant current supply is infinity. So what I am doing here, I am restricting the movement of electrons. I am limiting the number of electrons flowing out of the supply. So electrons will wait there till I supply the amount of energy I need. So I can supply 1 volt, I can supply 2 volts, 3 volts, 15 volts, 30 volts. So till that time electron has to wait there and grab all the energy. Then only it is allowed to come out of the circuit. So that's called constant current supply. So internal resistance of constant current supply is infinity. So continuation, constant voltage supply. What do I need here? Whatever may be the current, voltage must remain constant. So the energy supplied to each electron should remain constant. So if I ask 10 electrons at 1 volt, it has to supply. If I ask 100 electrons, it has to supply. If I ask 1000 electrons, it has to supply. So then it is more convenient to limit it to, so what is happening? So here it is supplying 30 electrons at 1 volt. It is supplying 6 electrons at 5 volt. So if I limit it to least possible voltage, least amount of voltage, I can grab more electrons. Right? So the internal resistance of constant voltage supply should be 0. Then once the electron gains little amount of energy, it will simply escape through the escape out. So and also we need very heavy, very low resistance, so that we need a express highway. How many ever number of electrons that come, the circuit should allow. So the resistance should be very minimal, it should be nearly 0. Then what happens? The path can now tackle 1 electron, 10 electrons, 1000 electrons, how many ever number of electrons you are asking, it will be able to pass through. So that is constant voltage supply. So the internal resistance is 0. And this can be replaced with a bypass resistance in parallel. సో ఈ పాత్లో ట్రావెల్ చేయడానికి ఇన్ఫైనైట్ రెసిస్టెన్స్ అడ్డం ఉంది అనే స్టేట్మెంట్ని దెర్ ఇస్ అన్ ఆల్టర్నేటివ్ పాత్ విత్ లో రెసిస్టెన్స్ అని కూడా చెప్పచ్చు. రాజుగారి చిన్న భార్య మంచిది అని చెప్తున్నాం. ఓకేనండి. సో దెర్ ఇస్ అన్ ఇన్ఫైనైట్ అపోజిషన్ ఇన్ దిస్ పాత్ can be renamed as there is a bypass on the other way. So a constant power supply in parallel with a low resistance can be called as constant current supply. So I'm bringing both of them onto a common platform. So now comes Thevenin and Norton theorems. So any complex circuit, let's say you are given a circuit like this, R1, R2, R3, RL, that is a load resistance. Let's say this is your TV or a radio. So you have a power supply, you have a complex circuit in between, and at the end you have a speaker. So whatever voltage you are supplying here may not be reaching that. Let's say this is 5 volts, and at the end this might be working at 3.7 volts. So in between some voltage is dropped up. So this entire complex circuit can be reduced to a constant voltage supply in series with a resistance. That voltage is called VTH and resistance is RTH. This can also be replaced with a constant current supply in parallel with a resistance. That is the basic statement of Thevenin theorem and Norton theorem. So any complex circuit can be reduced to a voltage supply in series with a resistance or a constant current supply in parallel with the resistance. So then how to get the value of this VTH? So the resultant voltage or the Thevenin voltage is obtained by removing the load resistance and measuring the voltage across the open terminals. So here you are measuring voltage across open terminals. Okay, so VTH is obtained by connecting a voltmeter, remove the load resistance and connect a voltmeter across open terminals. that particular voltage reading is VTH. And what is that value? It is a voltage drop across R2. So that is given by, so VTH is equal to VR2, that is VR2 by R1 plus R2. So what are we doing here? We are measuring the effective voltage seen by this load resistance. So we removed it and placed a voltmeter there. So after crossing all these resistances, some voltage is reaching to this level. So that is the value we are measuring here in the voltmeter. What about resistance? So this is VTH. What about RTH? So to measure the resistance, we have to replace all the supplies with their internal resistance. So we have to replace the voltage supply with its internal resistance and measure the remove RL. Measure resistance across open terminals. समझा we have to replace the voltmeter with its voltage source with its internal resistance. Internal resistance of voltage source is 0. So I am replacing it with a wire. So now if you measure the resistance from here, so RTH is R3 plus R1 R2 by R1 plus R2. This IN is given by VTH by RTH and RN is equal to RTH. So if you want to show this internal circuit as a current source, this is Norton theorem. IN is equal to VTH by RTH and RN is equal to RTH. So what is that? So IN is equal to VR2 by R1 plus R2 by RTH, R3 plus R1 R2 by R1 plus R2. So that becomes VR2 by R1 R2 plus R2 R3 plus R3 R1. That's all. So to work out this and Tina, we'll see in the next session.